let's
They
start.
don't want you to work.
No, they want, exactly, want the attention, want the
Yes.
attention. You stay outside the whole day. Now it's my time.
My time, yeah.
My time. That's it. Okay, so let's put this in the. Yes, so YouTube done. So today I'm. Okay, under 2 people. 1, 2, 3. Oh. Actually, today I had some student at home, and some student in class had to use the microphone for karaoke to give lecture. For people at home could hear me when I was talking in class and moving. One has to be creative.
Indeed. At least now I can hear you pretty well, like have no problems hearing you.
Yeah. Okay, so now look, 1 second. Jean-Luc doesn't have a video. There is the classroom and not the video. Where is? Okay. Okay, that's it.
Can you hear me now?
Yes. Yes.
Okay, good. Sorry, I had some issues with the thing this time.
So
Usual thing that the first day you come early, and then the second day you don't because everything works. But it didn't this time. But now I think I understand what I did wrong. Okay, let me just gather my notes.
So we have here on Zoom, we have our colleague is an algebraic, 1 second.
Oh, great.
Geometry, yes, we have Ilir. And we have Alessandro Arsi from Toledo University. So,
Great. Okay. Is it, everything looks good? You can hear me?
Yes, we can hear.
See, the image is different from yesterday. I don't quite understand the settings of all this. It's much closer. It's probably this. Yeah, okay, I didn't realize it was a setting like this. Ooh, nice. Look at that. You good?
Yes, we're all set.
Okay.
So we can maybe, 1 second, I forgot to get that I have these things that the computer, they all do different times. So 1 second, I take my.
Yeah, I'm just gonna write stuff from yesterday.
Yes, 1 second. Second, I lost the cell phone, so I don't know what exactly time. My computer is changing the time. Weston, do you know what time is it there? Exactly.
Now it's 7 p.m. and 3 minutes.
Ah,
Right.
okay. So the 3 minutes I'm interested. Okay,
Yes.
that's it. So I know how to adjust my clock. So I think we can start whenever. Shall
I'm
we?
ready.
So okay. So I guess just
Are you're recording?
Yes.
Everything? Okay.
yes. I'm going to record. 1 second. I'm going to record.
I need to say okay.
Once I don't know what. 1 second. Why is not record this computer? Record. I don't know. There's something doesn't want to disappear the bottom. 1 second. Usually there is just the bottom. It disappear the bottom. It's kind of in the meantime getting new people. I don't know why I lost the recording button. What? It's very strange.
Oh, is it because you gave me a host, maybe?
No.
Because I have a
Because
record button.
You have a record button. Okay,
Yeah.
so you record. So maybe give me back the host.
Yeah, I think it says your host.
It's very strange. I'm host. So if you have a record button, record. You can record, and then you pass me the link.
All right.
Okay, so we have a pleasure to hear again a wonderful lecture from Jean-Luc. Actually, Jean-Luc, will be interesting to just to say 2 words your path, because I forgot. The first lecture of the students, somehow they like to know how you got to do what you do, you know, what kind of background. If you can just spend 2 words.
Okay. Yeah. So yeah, I did my PhD in Texas, in Austin, in physics and in plasma physics, but with a kind of strong specialization in Hamiltonian, field theory, basically infinite dimensional Hamiltonian systems. And then I did a postdoc at Columbia with a plasma physicist, kind of studying the interface of fluids and plasmas. And that's what made me kind of transition a bit more into the fluid dynamics world. And after graduating, I had trouble in the US, the physics community, the physics departments, they don't do much fluid dynamics in the United States. And so I was luckier to find a job in England. So I ended up at Imperial College in the math department as my first faculty job. And so that's really what transformed me into a mathematician. I didn't change what I did all that much, but on paper, I went from being at a physics department to being in a math department, which also meant that when I decided to move back to the US, now math departments would consider me, right? Whereas before that, it was, math departments find it harder to look at physicists and things like that as potential hires. But if you come from a math department, then by now people have forgotten what my PhD was in some sense. So I think career-wise, I've drifted steadily kind of more mathematical, I think, over time. And so because I was interested in mixing, I was naturally led in the early 2000s by looking at these papers on the fluid dynamics of mixing, and in particular, these topological approaches. And so it took a long time to kind of teach myself all of these topological tools, starting from really nothing. But in the end, it was very rewarding, right? I'm glad that I learned all this stuff. It's nice also because it's a fairly unique skill set in fluid dynamics. Not many people know these topological dynamics sorts of tools. So it's, for me, it's proven very useful. Stefano, I'm not sure if that's the kind of thing you wanted, but
yeah, perfect.
Kind of thing you got.
Yeah, perfect.
Okay, so right. So yesterday we talked about, well, I showed you pictures of these mixing devices and these taffy pullers that somehow achieve this exponential folding of curves. And exponential is good. And maybe I didn't quite say it, but one reason why exponential is good is because if you have two fluids, then the interface, if you have two fluids that can react to each other in some chemical engineering application, then the interface between those fluids is a curve in 2D at least. And so the rate of growth of that curve is exactly the intermaterial contact area between the two reacting fluids. So for increasing reaction rates, it is important to kind of make this interface grow as rapidly as possible. And if you can get it to grow exponentially, then that's pretty much the best you can do. And what I then introduced was the idea of mappings of a surface to itself, homeomorphisms and diffeomorphisms, and then curves on those surfaces. So closed curves in particular, what we call loops, are an important object of study on surfaces. And in particular, the fundamental group of a surface is in some sense the space of loops on that surface, up to equivalence, up to homotopy. And then we started treating the simplest possible surface from the point of view of topology is the torus. So periodic boundary conditions. And we use as the torus a model where it's just a square. And then we would naturally think of closed curves on the torus. So for instance, a closed curve could be something like this. Notice that it's closed because it starts and ends at the corner, and the corner is all the same point, right? If you identify periodic boundary conditions, there's only one point on the corner. And so this would be our base point x0 for the elements of our fundamental group. And this particular loop, we would denote as 2 1s, right? 1, 2. Because it goes twice, it wraps twice around the vertical direction for only once around the horizontal direction. And these are oriented loops, so this is +1. But if you reverse both signs, you get well, if you reverse both signs, you actually essentially get you get the reverse loop, right? The opposite direction. Okay. So then we started looking, how do you classify mappings of the torus to itself, homeomorphisms or diffeomorphisms of the mapping of the torus to itself up to homotopy again, so equivalent or isotopy, right, as I have defined. In particular, I tried to convince you that what you really want to do is to look at the action of a map on closed curves. So, and we eventually concluded that the action induced by some diffeomorphism phi of the torus to itself, the action of that mapping on the fundamental group of the surface. So on pi1, the pi1 is the fundamental group of the torus. It's the space of loops based at x0, that the mapping could be expressed as a 2x2 matrix because any element of pi1 can be expressed as a 2 vector. So then we said, well, let's write down the most general matrix that we can. Of course, it's not totally general because it has to be an element of SO2 or SO2Z. So it's 2x2 matrices with integer entries and unit determinant. And I explained last time where that all came from. The fact that it's got unit determinant is because it needs to be invertible, but its inverse also needs to contain only integers, because its inverse is also a diffeomorphism because of the definition of the inverse of phi is also a diffeomorphism. The next step was to look at the characteristic polynomial of this 2x2 matrix, which looks like this, where tau is the trace of the matrix and 1 is the determinant of the matrix. This has eigenvalues x plus or minus, so tau plus or minus tau squared minus 4. And this tau squared minus 4 square root suggests that something interesting happens when tau is equal to 2 in absolute value. So at the very end of last lecture, we considered the 3 possible cases where the trace of the matrix is less than 2. So that means it can only be -1, 0, or 1. And in all 3 cases, we concluded that some power of the matrix was the identity map. Okay. In particular, you can pick 12 as the lowest sort of common multiplier that guarantees that some power of the matrix is going to be the identity. So for tau less than 2, every single matrix is so-called finite order or elliptic, meaning that after a certain number of powers of phi, you get back where you started. And I want to emphasize again that it's important to know that this is a topological claim up to homotopy or up to isotopy of maps. Because it doesn't mean that phi to the 12 is the identity. It means that phi to the 12 is homotopic or isotopic to the identity, meaning you can, whatever image you get of the surface under that map, you can retract it, you can deform it back to being the identity map, which is the best we can do unless we specify more information. It's the best we can say in the topological setting. Okay. So where we're picking up now is to consider the other cases. And clearly the next case is tau is equal to 2. Or tau is equal to plus or minus 2, right? So there's only two possibilities when tau is equal to 2 and the trace of the matrix, which again, tau is just A plus D. So if tau is equal to 2, notice that my eigenvalues are tau over 2. We have a degenerate pair of eigenvalues, right? And we can use the Kaylee-Hamilton theorem again. Remember, our Kaylee-Hamilton theorem says that m squared is equal to tau m plus I. Okay. So if tau is equal to 2, then we can rewrite, let's see, we can rewrite this as a squared, right? If this is plus or minus 2, then notice that I can bring everything to one side and write this as m minus plus I squared is equal to 0. So again, m minus plus I all squared is equal to 0. Okay. So this is interesting. This is a matrix on the left, and its squared is 0. It doesn't mean that the matrix is 0. It just means that this is equal to a matrix that I'll call n, which is nilpotent. Or sorry, I guess it's idempotent. Nilpotent, right? It's idempotent. The squared is equal to 0. Okay. So no, nilpotent. N squared is equal to n is idempotent. Sorry. Right. So in other words, we can write m going back here to say that m minus plus I is equal to n. So this is. So the matrix M is some plus or minus identity plus a nilpotent block. Okay. So this is not the same as finite order because you can keep taking powers of M and you will not get back to where you started. Again, as I said last lecture, the whole idea of dynamics is to keep doing the same thing over and over again. And for us, it's acting with the matrix M over and over again. So something fairly simple will happen when we take powers of M, but you'll never actually get back to where you started. So for instance, what's an example of a nilpotent matrix? Well, you could imagine taking 0, B, 0, 0. That's a matrix whose squared is 0. Right? If you have an upper triangular matrix in 2 dimensions, then its squared is 0. It has zeros on the diagonal. So the matrix M, for instance, could look like this. Right? It could look like plus or minus 1, B, 0, plus or minus 1. So that is a matrix that satisfies all of our requirements. Its determinant is 1. And it's not that the squared of M is identity, right? If you keep taking M squared, you can work out that you'll get, let me just take plus 1 for simplicity. I think you get B plus 1 here, right? If you square B, you're basically adding, if you square M, sorry.
We are at the limit of
do I need to? Thought I'd zoomed it out enough. Thank you. Let me just check my image. Is that better? Okay. Are you still there?
Yes, we're here.
Okay, good. I was worried that I screwed something up by touching the remote control. Right. So m squared is b plus 1, and in fact, m to the n would be b plus n plus 1 or something, right? B plus n minus 1. So you're incrementing one entry of this matrix each time. So let's just draw a picture of how that thing acts in practice on our torus. So for simplicity, let's take m to be 1 minus 1, 0, 1. I might have screwed this up. I don't know, maybe I did. So then m squared, let's consider m acting on an element like 1, 0. So what's m times 1, 0? Well, it's going to be, 0, 1. M acting on 0, 1 will be, let's see, minus 1, 1, right? And then m squared acting on 0, 1. Let's see, you now take 1 times minus 1, so that's minus 2. 1. You can maybe see the pattern, m cubed acting on 0, 1 is equal to minus 3, 1. So what does that mean as far as our loop is concerned? Well, it means that we're winding the loop ever more tightly across one direction of the torus. So if I start with my model for the torus as a square, and I think of 0, 1 as my loop, that's a vertical loop like this. Okay. So let's call this x. That's x. So then if I do m squared on that loop, I will get something like that, something that goes in minus 1 in the horizontal direction, but plus 1 in the horizontal direction. So something like this, I guess. Right? I should draw this in yellow just to agree with my previous picture. So that's minus 1, 1. 0, 1. And then the next image is minus 2, 1. That's something that winds twice in x, but only once in y. And so if you draw it, you can see that it's going to be something like this. So that's minus 2. So you can kind of see the pattern. What I'm doing is I'm twisting the loop. The loop is wrapping more and more times around one direction of the torus, while leaving the winding, around the other direction fixed at equal to 1. So those are very special elements. They're called parabolic elements, just like the other one was called an elliptic element. This is a kind of boundary case. So this sort of element is called a parabolic element of the mapping class group. Parabolic elements will have the following feature. First of all, they're not finite order, which means that if you keep taking a power, you don't get back to the identity, but you also don't get exponential growth. So if you satisfy both of these requirements, you're essentially in the class of so-called parabolic elements. And in fact, there's some of the elementary ones are called Dane twists. So for instance, the one I drew over there, and another one, these two triangular elements are called fundamental Dane twists. Okay. And you can see this is the upper triangular. I put a minus 1 there, that's just a convention thing that doesn't really do anything. And then the other one is the lower triangular version. Okay, and the reason why these are important is that together they generate all of SO2Z. In other words, any 2x2 matrix with unit determinant can be written as some product of these two matrices and their inverse. It might be a long sequence, but every single element of SO2 can be written as some product of these. And that'll turn out to be important later when we talk about the braid group. Okay. Just to look ahead a little bit, these matrices will be identical to the action of braids on the disk. It will be related to the action of a braid on the pins of our taffy polars that we saw at the beginning of the first lecture. Okay. Let me just make sure that I haven't forgotten to say anything. Right. I think we're good. Okay. Any questions before I move on to the third and final case?
May I ask you something, Professor Thiffeault? I'm sorry, but the third example I didn't understand quite well. Why is it the two lines, the line going vertically like 2 times on the y-axis and just once in the x-axis, and not the opposite, like going twice in the x direction and once in the y direction? I kind of lost it.
It could be that I got it. It could be that I got it wrong. I think I might. Did I get it wrong? I always get that picture confused in my head. So if you think of this as the x-axis,
yes,
this is indeed wrapping twice, right? Does that make sense?
Because I understood that it's going twice in the y-axis, but okay, if you say so.
Like if you imagine following the loop in this direction, right?
Okay,
it goes, or the x direction is like this direction, right?
yeah, okay.
So it goes down, back up, and then back down.
Okay.
So it's wrapped twice in the x direction.
The x direction. Okay. Okay.
Yeah.
Now I got it.
You know,
sorry.
to be honest, it's just a conventional thing, like in the sense that you could probably make sense of it either way. But that's the current interpretation that I'm using. Hopefully I didn't get it backwards. I tend to get confused about these things very easily.
No, but I understood. Sorry. I apologize.
It could be that I did it backwards, to be honest, from my notes. I find it very hard to convince myself one way or the other. I always get confused. I always have to look it up. But, you know, let's just take it as morally speaking, that's kind of what's happening.
Okay. Thank you very much.
Sure. Okay. Okay. Oops. So what about the final case? The final case is any trace of the matrix which is bigger than 2. Then what happens is that the two roots, x plus or minus, that I wrote before, which are equal to half tau plus or minus root of tau squared minus 4, those are now 2 real numbers. Okay. Right, because it was 2 distinct real numbers, right? For tau less than 2, this was an imaginary number, but we used the Kaylee-Hamilton theorem to avoid talking about complex eigenvalues. For tau is equal to 2, then it's real eigenvalues, but it's a degenerate pair. For tau bigger than 2, you have 2 distinct real eigenvalues. So that means that now it kind of makes sense for us to start thinking about diagonalizing the matrix, perhaps. Again, we could have done this in the complex case, but it's easier not to do that. So let me define a number lambda to be the kind of biggest one of these eigenvalues in magnitude. So it's actually going to be absolute value of tau plus root of tau squared minus 4. Okay. Because it could be that tau is minus 20, right? In which case the biggest eigenvalue in magnitude is the negative. So this number is going to be called the dilatation, or the dilation, or the growth, or the expansion factor, or the stretch factor. It has many, many different names in the literature in the concept of Anosov maps. So the two eigenvalues, in other words, are equal to plus or minus lambda and lambda inverse. Because of the unit determinant, the product of the two eigenvalues is always equal to 1. So either both eigenvalues are positive or both eigenvalues are negative. Okay? So the plus or minus here is the sign of tau, the sign of tau. Okay? But lambda itself is always defined to be positive. In fact, you can even see that this is bigger than 1. Right? Because tau is bigger than 2, this thing is bigger than 1. Because, you know, as you limit tau to 2, this is 1, but then you're adding something non-zero to it. So this is strictly bigger than 1. So what kind of number is lambda? Well, it won't surprise you that this is an irrational number. Right? Well, actually, you might worry that maybe for some values of tau, this could be a, you know, this radical might not be an irrational number. But in fact, this never happens. If you take a squared minus 4, you never get you never get something that's rational again. You can show this. Actually, it's an interesting little exercise. One way to show this is to compute the continued fraction expansion of lambda, which you can easily do by using the characteristic polynomial itself. Because if you think of the characteristic polynomial, if you multiply it by x inverse, it tells you that x is tau minus x inverse, right? So I just solve the characteristic polynomial, and then I can use this to actually generate the continued fraction representation of lambda. So I can show that lambda in continued fraction representation is tau minus 1 plus 1 over tau minus 2 plus 1 over tau minus 2. Something like this. But you can easily show that the continued fraction representation it never ends, right? It is periodic actually, but it never ends, which is the hallmark of an irrational but algebraic number, right? The fact that this sequence of numbers here is periodic, it repeats itself, but it never ends. So lambda is an irrational number, which is not very surprising. What that means is that if I compute the eigenvector of the matrix, so remember we have our matrix M, and the two eigenvectors can be written plus or minus lambda minus d, c, and plus or minus lambda inverse minus d, c. That's one way to write the two eigenvectors. And one of them will be associated with plus lambda, say, and minus lambda inverse in the case of tau positive. What's important here is that the lambda shows up in the eigenvectors along with the integers, but that does tell you that the slope of the eigenvectors is irrational. So if I draw, the question is, what is the loop associated with this?
Jean-Luc,
yeah.
one second, because I didn't. Can you make it a little bit bigger? When you write the eigenvector, I cannot see.
Sure. It's not. Yeah. Let me just.
It appears very small.
Sorry. Yeah. It's not the best audiovisual setup. The one eigenvector is plus or minus lambda minus d, and then c. And the other one is just replacing lambda by lambda inverse. Okay. Is it reasonable now? Can you sort of see?
Yes.
Okay. So again, my point is that this lambda here means that the slope of the eigenvector, the direction that it defines in the plane, is an irrational number, which means that if you try to draw it as a loop, right? Let's say you try to say, well, this is going to be some kind of loop. you can't do it. It is not in the space of loops because it doesn't have, you can't multiply by some common denominator to turn it into something involving two integers. What it is a funny curve that just keeps going. I'm trying to draw it in an honest way, but you get my idea. That this thing keeps wrapping around the torus, but it's never going to bite its own tail, because if it did, it would be a rational number, right? If there was some multiple of number of times going this way, and number of times going this way, that you came back to your tail, that would have the implication that this entry here is a rational number. And we already know that lambda is an irrational number. Okay. So this means that this eigenvector is not in the class of loops. And so therefore, we can't really diagonalize our matrix in the way that we were hoping with. We can't really pick some representation where we're picking a basis for the loops in some sense, right? This is not a legitimate basis to transform into for the space of loops. But dynamically, what's happening, if you remember what happens to a matrix, when you take a large power of a matrix acting on some vector, in the limit as n goes to infinity, what happens is that this will align with the eigenvector associated with the largest eigenvalue. So let's call this u here. U is the unstable eigenvector, so it's the eigenvector associated with the eigenvalue that has, with the eigenvector that has the eigenvalue lambda, where lambda is the largest of the two eigenvalues. So roughly speaking, that means that this will go as lambda to the n times u, right? In the sense that if I start with any initial loop x, which is a vector of integers, but I take the limit of very large m, then asymptotically, the image of m to the n times x will be dominated by the largest eigenvector, right? Because the other part is plus lambda to the minus n times s, where s is the stable eigenvector. So that'll go to 0 as n goes to infinity. So what that's saying is that this loop might not be a true loop, but any initial condition will try to align with this unstable direction. So a real loop will be something that is actually closed, right? But somehow comes quite close to the actual eigenvector. But the difference is that it eventually does close. I mean, it's obvious what this is. This is a rational approximation to an irrational number. And you all know that you can approximate an irrational number as well as you want to an irrational one by just taking a bigger and bigger denominator, right? By allowing yourself to use bigger and bigger rational numbers. However, note that the length of this loop will actually grow exponentially at the rate lambda to the n. So this is why lambda is the most important quantity in all of this. I told you that lambda was bigger than 1, again, because of its definition, because tau is bigger than 2, right? So this is bigger than 1, and then you're adding something bigger than 0, so you're getting something bigger than 1. Okay. So we conclude that for this class of mappings with trace bigger than 2, these are called the hyperbolic elements. And for the hyperbolic elements, if you repeatedly act on some initial loop, no matter what the loop is, it will eventually grow exponentially. Well, not even eventually, it will immediately grow exponentially in this case. In some cases, it might have a transient. It could shrink on the very first iteration, but then keep growing or something. Notice that there's no loop that can be fixed by this, right? Because if there was a loop that did not grow, then it would be an eigenvector of this matrix. And we already know all the eigenvectors. There's one that grows and one that decays. So there cannot be any kind of fixed loops under the action of this map. All loops will eventually grow. And it's not possible to have a loop that only shrinks because S, the stable eigenvector, is also irrational. So there's no way to exactly represent a loop, to use a loop to exactly represent S. You might approximate it very well, but you'll eventually have to grow away from it. Another interesting observation is that M inverse will reverse the role of U and S. If I act backwards with my map, then because the eigenvalues of M inverse are just lambda and lambda inverse swapped, so they're the same thing again, and U and S are also swapped. So this is the important observation that if you iterate backwards in time, so if you pick a minus n direction, then your loop will align with the complementary stable direction, which is not necessarily perpendicular to U. It is if M is a symmetric matrix, but in general, M isn't. Okay, so that was a lot of information at once, but maybe let me pause and ask if there's any questions about clarifications. Okay. So the simplest example is very famous. And if you've taken any kind of dynamical systems course, you perhaps saw this very famous map, which is called Arnold's cat map, which just consists of the entries 2, 1, 1, 1. You might think that there would be a way to do something even simpler by having some zeros, but having zeros is actually quite difficult, right? Because if I put a 0 here, notice the determinant of the matrix has to be 1. So if I make a 0 here, then the determinant is just the product of these two numbers. And if you want that product to be 1, then you can't have the trace being, the trace will have to be exactly equal to 2. Okay, so it's not possible to do this by putting a 0 on the off diagonal, and therefore the Arnold cat map is about the simplest thing you can do to have a matrix whose trace is bigger than 2, but whose determinant is actually equal to 1, right? Because 2 times 1 minus 1 times 1 is 0. And famously, in that case, the dilatation, so the largest eigenvalue, is equal to 1/2 3 plus square root of 5, which is the squared.
Jean-Luc, there is a question.
Yeah, just a sec.
Yes.
So 3 plus root 1/2 of 3 plus root 5 is actually exactly the square of 1/2 of 1 plus root 5, which is the golden ratio of squares. All right, it's 5. So the Arnold cat map is a sort of very distinguished object with a dilatation or an expansion constant or a growth, its largest eigenvalue, equal to exactly the golden ratio squared. Okay, question, yeah.
So Victor is asking, would you mind explaining the stability of the eigenvector? You know which one is stable or not? The value of its associated lambda? Yes, exactly. So that's just a definition, right? There's a lambda bigger than 1, and there's two eigenvalues, right? X plus and minus, and lambda is the magnitude of the largest one. Okay, so I will take the one with the largest magnitude, and I will call that one the unstable direction, and then I will take the one with the smaller magnitude, and I will call this one the stable direction. And the distinguishing feature is one has an eigenvalue which is bigger than 1 in absolute value, and the other one is an eigenvalue which is less than 1 in absolute value. And the reason why I know that that has to be the case is because the product of the eigenvalues has to be 1, because this matrix has the determinant 1. So there's always going to be a direction which is unstable, and there's always going to be a direction which is stable. And the distinguishing feature is whether the eigenvalue is bigger than 1 or less than 1. Does that make sense? Yeah, we're happy. Okay, good. Sorry, I can't look. My laptop is way over there, so I don't really see what's happening on the laptop. Okay. Okay, so the point is you approach this stable direction, but which has an irrational slope. Okay. So again, just to foreshadow a little bit, we're actually very close to the taffy puller.
some sense, or to the mixing device that I showed. Maybe I should show the movie again, just because I think you know, you will incrementally understand better and better what it means to see that movie. So let me just show you again. That's the sec was there. Okay. So this is the movie that I showed yesterday of the mixing device with the rods moving. And again, I mean, you're not yet in a position to know what to understand the details of this, but I will tell you that this curve that you see there is very analogous to one of our loops. It would be exactly a loop if it was actually wrapped around the rods, but it isn't. But what I want you to focus on is the fact that it's approaching a fixed pattern, right? If you look, it does seem to be kind of converging to some, you know, canonical Platonic pattern underlying the whole thing of streaks. That pattern is exactly the same object as my unstable direction, as my unstable eigenvector. And just like for the torus case, my mixing pattern here is trying to approach this, which has infinitely fine structure, but it will never quite get there, right? Unless, of course, there's diffusion and other effects, etc. But mathematically, it is trying to align with this direction in some sense. The difference, of course, is that for the mixing device, we're not on the torus, and things are a little bit more subtle, right? In the sense that it's not just a question of looking at the linear action on the map, but I'll try to convince you by the end of this lecture, maybe, that they're kind of the same thing. Okay. You can see the board again, right? Yes, you can see it?
Yes.
Yeah. Okay, any other questions? Okay, so now I would like to explain this relationship between the torus and the space of our taffy puller in some sense, of our mixing device that we just saw. So let's go back to our model of the torus. Okay, so this is our torus, and I'm going to be a bit more specific. We actually have axes, right? We have 0, 1, 0, 1, and since this is actually a periodic section of the XY plane. Okay, and let me define what I would like to do now is to go from the torus to the space where my mixing device is going to live, which is a punctured disk, a disk with some special points that as you saw in the video, these points are kind of moving around. Right? So how do I make a construction where I go from this torus space to this disk? And it turns out that the important object is a little map called iota, right? The Greek letter iota or iota, which is a map from the torus to itself. And iota is going to be the simplest map you can imagine. Iota of x is minus x. That's all. Okay. Iota just kind of takes my torus and, well, what do I mean when I say minus x, right? That's a bit of a tricky thing because my torus lives between 0 and 0, 0, 1 and 0, 1. So I have to tell you that this is mod 1, right? So I take modulo an integer in every direction. I only keep the positive fractional part of this. Okay. So I'm not telling you yet why this map is interesting, right? Minus the identity, but let's just study it a little bit. I claim that it has 4 fixed points. Anybody see what the fixed points of this map are? mean, there's one trivial fixed point, right? 0. Right? If I say iota of 0 is going to be minus 0, so the origin is a fixed point. Of the map iota. Fine. But I claim that there's actually several other fixed points. For instance, consider the point 1/2 and 0. Okay, what is iota of 1/2 and 0? Well, remember iota is just minus the vector. So it's minus 1/2, 0. But I have to take mod 1. In other words, I have to add any multiple of an integer that I want to make sure that the answer is in the unit square. It's from 0 to 0, 1. So notice that the only way to get minus 1/2 to be back within 0, 1 is to add 1. So if I add 1 to 1/2, I get to minus 1/2, I get 1/2. So I can update my picture here, say that 1/2, 0 is actually a fixed point. Okay. So now maybe you can see where the other fixed points are going to be. Because the same thing happens for 0, 1/2. And finally, 1/2, 1/2, right? If I just take the center point, it also gets mapped to itself. So the map iota has 4 distinguished points, distinguished fixed points. Okay. So far, so good. Please interrupt if there's any ambiguity. Okay. So these 4 fixed points are going to play an important role. We'll give them some names. We'll call this one 0, and then 1, and then 2, and then 3. So in particular, I'll call them P0, P1, P2, and P3. That's just defined counterclockwise. Okay. Right. So let me now construct what's called a quotient space. Call a new surface S, and S is going to be our torus modulo iota, or quotient iota. What does that mean? If you've seen this concept of quotient spaces, what it's saying essentially is that my space will still be the torus, but if there are pieces of the torus that are related by iota, then those only count as 1 point. So I'll give you an example. Iota maps, say, this point to this point. Right? Because again, you do minus this point, but then you do mod 1/2, and you get back to this one. So as far as iota is concerned, these are exactly the same point. So how do we draw this surface? I'm going to make a very big picture. Try to do this. We have 4 distinguished fixed points. But let's try to think of what happens to the lines in between those fixed points. So for instance, if I draw this curve and I give it a little arrow, where is this curved map under the action of iota? Well, the thing to do is to look at individual points. These are fixed points, so those don't move. And then if I consider this little tail point here, it gets mapped to this tail point here. So I can draw my arrow. So under the action of iota, this little segment here gets kind of reversed and now points this way. Okay. By the way, iota might, I just said it reversed a curve, but it's still it's an orientation preserving map because it does two reversals, right? Its matrix representation as an element of pi1 is -1, -1. So the determinant is still +1. So it's still an orientation preserving curve. In other words, it maps a little system of axes to another system of axes, which is still right-handed. So it's orientation preserving. So let's keep going. As you can imagine, it also maps this segment to this segment. Okay. Does that make sense? So now I like to represent, in fact, what it does to the interior by using letters. And you've got my notes, perhaps you've got access to them, but let's say there's a big A drawn here. Then iota is going to map it to this quadrant, but because it also does a minus sign, it's going to flip the whole letter. And so it's going to map the A to sort of a upside down A. Okay? And it's going to map a B here to an upside down B. It's really a rotated B, right? So notice that there's now two copies of the same thing, right? This whole upper part is just duplicating the lower part because they're identified by iota. So that means that my surface S, my quotient surface, and it can be identified with only half of the space if I want, right? Again, I'm sort of, I'm identifying points of the space which are related by iota, and therefore once I figured out which points are related by iota, I only need one copy of these points. So all of the points above, I could choose to throw away this or throw away that. That would be exactly the same surface. I can cut my surface in many different ways, but I'll choose to cut it by deleting the top half. And what is left is the surface S. Okay. So that's a construction of this quotient surface. Now, what surface is it, right? What is it that we have created for ourselves by doing this identification? Well, let's keep going a little bit and draw more arrows. Notice that under iota, this bit would get mapped to this bit. This is not periodic anymore because we've chopped away the upper half. So there's no reason why this is identified with this. But the sides are still identified. Okay. I need more. There we go. The sides of my surface are still the same because that's still periodic, right? I haven't chopped in that direction. So now, what kind of surface is this? Well, I'm going to start destroying these identified edges. I'm going to start undoing them, if you will. Think of this as a flattened thing, right? I've pushed it onto the plane. It's also called a flat surface sometimes in the literature. So I can unflatten it, if you will. Notice that the fact that this arrow is identified with this arrow anchored at this point means that I can kind of zip, right? I can take my two curves here and I can start identifying them together like this, right? So I can start zipping as I go along, and I will eventually get to this picture. Which will look like this. Again, there's a little arrow pointing to the right here, pointing to the left here. I have now glued them together into one downgoing arrow, and I've glued together my two upper arrows here, my two double arrows, into one upgoing arrow. Okay, and I still have my big arrows on the sides. Okay, so I'm deforming as I go along because there's no real, it's topology. I don't really need to preserve the metric, right? My distinguished points at the ends are still there. So my 4 distinguished points are still here. My fixed points of the map iota. Okay. If you want, I can also write down my A and B. My A is here and my B is here, right? Except now I've deformed them a bit because I'm starting to zip things up. Okay. So I'm almost done, but notice that this edge is still identified with this edge. So I want to zip those two together. But the only way I can do that is by lifting the whole thing off the blackboard and gluing them behind. And so I think you can maybe see that what we're getting is actually a sphere. Surprisingly, right? By doing this iota identification on the torus, the topology of the resulting surface is actually a sphere. I can zip behind this thing and I'll get something shaped a little bit like an American football, right? It'll be glued behind and the whole thing will be kind of a long elongated thing. But of course, a football is basically a soccer ball. So in other words, a American football is basically a rest of the world football topologically. And so let me draw the final surface and we get all of it out of this. It'll be a sphere with 4 distinguished points, which again we call 0, 1, 2, 3. This circle is meant to be a sphere. I guess I can draw maybe an equator or something. To emphasize that it's a sphere, that's not a very good equator, but roughly speaking, that's what's happening. And let me just write down P0, P1. So I still have my double arrow. So this is still 0, 1, 2, 3. And so from 3 to 2, I have an arrow going this way. So topologically, the surface S that I have created with this map iota, and iota is called an involution because its square is actually the identity. So it's an involution map. The surface that I've created is now a sphere, but it's a sphere with 4 funny points, which don't really play a role just yet. But spoiler alert, they're actually going to be the rods of my mixing device. Those special points are actually, you know, when you saw the movie earlier, those are going to play the roles of the rods in that movie. Any questions so far just about the construction? There's pictures in my notes. I don't know if that'll help.
Fine. Everything's fine.
May I ask a question?
Sure.
Professor, in your simulation, there was 3 rods.
Very good point. Yeah. Well, first of all, I can ignore a point if I want to, right? So it might just be that I don't care, but also I'm going to actually give it a special role. That's a very good question. The answer to your question is that the 0 point, right? I can think of sending it to infinity in some sense, in a following way. Let me take my 0 point, but instead of thinking of it as a point, let me open it up a bit. Let me make it a disk. Let me leave the other 3 points alone, but let me just take the 0 point and inflate it a little bit. But then I can keep inflating it until I actually get a disk instead of a sphere, where the boundary of the disk is the 0 point. And my 3 points look like this. Okay, so the 0 point in the simulations is actually just the boundary of the disk. In fact, it's still there, but it's kind of surprising, right? A boundary and a point are not so different if you allow yourself to cut the boundary a little bit, and then you realize that this is topology, so the size of things doesn't matter. I can stretch it as big as I want. And so again, think of this sphere as being rubber, and I make a little hole in the sphere, and then I stretch the hole out and I step on the whole thing so that it's flattened on the ground. So now what was a hole has become the outer boundary of my rubber ball. And there are 3 points left over. Okay. Does that make sense?
Nice. That also means that the boundary is fixed. Yeah.
Yes, which is perfect, right? It's kind of what we need. The boundary is the one point that never moves, right? And you'll also notice that on the torus, using our linear maps, the point 0 is the only point that never actually moves. 0 is a fixed point of every possible linear map. So it's a perfect place to put the boundary, right? Because the boundary of our disk will never move. We only want to remove the 3 rods. Yeah.
Nice.
Yeah, very good question. Okay. So if you think about it, even if you only have 3 rods, right, you need that 4th point. Because imagine that I drew a loop around two of the points. If I didn't have that 0 point, I could drag my loop all around the sphere and use it to create a different loop, right? So the 0 point is actually, think of it as a kind of North Pole where loops are not allowed to cross the North Pole. And it's preventing us from going behind the taffy puller. Like if you have a taffy pulling device, you're not allowing yourself to drag the taffy and bring it behind the whole device in order to unwind the taffy in some sense. So it's just a topological obstruction, and you can think of it as the boundary of the thing. But it's actually crucial. You need to have a point like that. Right. So let's think a little bit now about what happened, right, to our map iota in terms of acting on pi 1 is actually -1, -1, 0, 0. Okay? It just reverses the direction of my loops, but all of them, therefore, it preserves orientation, net orientation. But this is a very important form because there's something very special about minus the identity, right? And that is that it commutes with everything. So this is a non-trivial map, but it does commute with absolutely every 2 by 2 matrix that I can throw at it. This is important because now I would like to do the following. We have a picture where we have a torus, and we have a map phi from the torus to the torus. Okay, that's our original picture. But then we also have a disk, and maybe it's time that I give it a name. I mentioned this the last lecture, but this I'm going to call D3, the disk with 3 punctures. Okay, so how do I make a map from D3 to D3? Well, I can use iota. Iota is my quotient with iota, I guess. Let's call it pi. Pi is a projection map, right? Pi takes the points on the torus and projects them down to D3 using this construction using the quotient space. Okay, and then I can do the same thing at the end. Okay, so how do I make a map from D3 to D3? Well, I need to be able to lift here and then do phi and then come back down. Okay, but an important component of this is that phi and pi always commute. So in other words, I don't affect anything by doing pi, phi, and then pi again. Because my involution commutes with the map, it means that every step this is well defined. It doesn't matter if I act with the map on the torus first, or if I act with the map on the disk first, in some sense. It doesn't matter when I do this projection, it's always well defined. Now there's a small problem. To go back up, you have to be a bit careful because you've got 2 copies of the torus here. So you're not allowed to go, you're going to be doubling up the disk to get onto the torus, right? You'll necessarily have to duplicate your disk twice to get back on the torus, which means that not everything up here can be projected down there, right? Because if you don't have the same thing on your 2 copies of your torus, then it's not legitimate. So you have to be a little bit careful about what you mean by this projection. But the important property is the commutativity of iota with every possible linear map. What it means is that every possible M that I put up here can be descended to a map of the disk. In particular, let me show you what happens to a curve, and then I'll probably end there. So let's draw torus again. This is same model as usual. And let me draw a loop, alpha. We'll call it alpha. I chose to draw it off the axis because I want to be a little bit away from my points. So let's remind ourselves where our points, where our distinguished points are. 0, 1, 2, 3 are like this. So this curve is a curve that starts between 0 and 3, but 0 is the boundary. So let's not think of that. Let's think of it as starting between 1 and 2. So my curve kind of initially will be between 1 and 2. Okay. Then it needs to move along until it ends up between 0 and 3, but then comes back to between 1 and 2. So being between 0 and 3 is like being between the boundary and 3. So this curve actually does this. Actually, you can't give it an orientation because of the way the map is defined, right? Because you're really descending 2 copies. You really have a double curve here, and you're laying them on top of each other because of the identification. So let's not worry about orientation in this case. So this curve here, again, here is between 1 and 2, which is here. And then it winds its way around, passes between 0 and 3, and then comes back between 1 and 2. So topologically, it has exactly this shape. Whereas a vertical curve, so if I took a curve like this, on beta, it won't take you much imagination to believe that it passes between 2 and 3, right? And then between 0 and 1. So it looks like this. So these 2 fundamental loops here, and again, I can glue them onto the punctures if you want. I'm just trying to keep them a little bit away from the punctures to make the picture clearer. When I say puncture, I mean these distinguished points, right? So notice now that every curve on here, as long as it's iota symmetric, right? It has to satisfy some conditions. You have to be a little bit careful, but can be descended onto a closed curve on the disk with 3 punctures. Okay. And that's amazing, right? Because now it means that if I have a map that causes these curves to grow exponentially under iteration, in this picture, it will look like exponential growth of these loops. And that's exactly my taffy polar. That's exactly the picture of my taffy polar. In fact, the taffy polar that I showed you is roughly pretty much exactly the image of the map 2111 on the torus, but descended onto this punctured disk, this disk with 3 punctures. Right.
There are some questions.
Okay, I think this is probably a good point for me to stop. So I will stop and take questions.
Okay, so just before I forgot, let's thank Jean-Luc for the great lecture. So please join me, open the microphone.
Thank you. Thank you.
So Victor doesn't have a microphone and he was asking first, could you also perform this process via stereographic projection with base point being the 0 fixed point and then compactify the plane on which the projection was done into a disk?
A stereographic projection, you said?
Yes, a stereographic projection with base point being the zeros, that.
Yes.
Zeros,
yes. So what he's saying is you could also map the point 0 to infinity, right? You could make it into the Riemann sphere, basically. Yeah, and that's totally fine. Yeah. In fact, that's the way people usually think of the Braids group in particular. They don't usually have a boundary. It's only for the physics in some sense that I think of the thing as being a boundary. But absolutely, usually people think of this more as the Riemann sphere.
Yeah, and then he has another question or comment. Just as some sort of alternative construction of D3 maybe without having to deform the fixed point into a fixed disk. No, it's just an addendum to the previous one. Okay.
Yeah, exactly.
Yeah.
Exactly. Again, the disk is only for convenience, but it could be an open set. It could be a puncture, right? And then you would just map it to infinity. Exactly. Yeah. So that works just.
Yeah, he's happy. He
Okay,
said, "Thank, great lecture, Professor." So, other comment?
Yes, can I ask a question?
Of course.
Thank you, Professor. So you say before the then twists that are parabolic constitute a basis for all the matrices that we are working with.
Yes.
But you say also that the problem with the parabolic is that the increasing is say linear. The advantage of the hyperbolic is that it's exponential. But can I say that expressing in the basis of then twist, all exponential is composition of linear, something like that? I was thinking.
Yeah, so that's a very good point. I forgot to say that. First of all, I want to apologize. I remember now, I think I wrote SO2 in some places maybe, where I really meant SL2. So I don't mean the group of orthogonal matrices, right? I mean the group of determinant one matrices. So if I wrote SO2 somewhere, that was wrong. But I can give you the example of 2111, right? So that's a hyperbolic element, we all agree. And it can be written as the product of 1, I think 0, 1 times 1, 0, 1, 1. So that's 2, 1, 1, 1. So if I take the upper triangular matrix 1, 1, 0, 1 times the lower triangular matrix 1, 0, 1, 1, those are two parabolic elements with trace 2, but their product is a hyperbolic element with trace 3. So I don't know if that's the question you were asking. In other words, the product of parabolic elements can easily give hyperbolic elements.
Yeah, that was, I think it was that hyperbolic meets in an exponential rate, but so parabolic, yes. Parabolic meets like in a log rate, something like that, because.
Yeah, linear in this case. In this case, it ends up being linear. Yeah.
Okay. Thank you.
Thank you. There's in fact a physical fluid dynamics consequence to this, right? That it's well known that to mix, there's a whole book by Rob Sturman and Steve Wiggins and Julio Attino on the linked twist maps. Twist maps are maps where you do one thing in one direction and you do the other thing in the other direction. And it turns out that this is a very effective way of mixing because you cross the streamlines of the flow. And this, of course, what I'm doing here is all at the level of topology, but even in the practical level, it turns out to be a very good idea to intersect yourself. So when you're cooking, very often you're stirring something like a paste, and you find it useful to do something like a figure 8. That means that you're bisecting your previous motion. That is actually quite similar to the multiplying of these two triangular matrices. Individually, these two motions are not very good, but if you compose them together, you get a folding effect, which is really the essence of chaos. So we shouldn't be too surprised in some sense that the product of two parabolic elements is hyperbolic, because that's, even intuitively, we do that in everyday life.
Nice, thank you.
Yes, other questions? Yes? No? So, well, very nice. Very geometrical. So thank you very much.
Thank you.
Jean-Luc.
Yeah,
thank you for the great lecture.
I guess I'll see you on Tuesday.
Yes, on Tuesday again. So, and if you could then upload and send us the link to for the registration, since it's on your computer. No? Hello?
Sorry, is it?
Yeah, I think, no, it's not on mine.
Oh, well, for the recording.
Yes.
sorry, I think you said registration, but I think you mean
yes, recording.
okay. Yeah, I'll send you. I think I recorded locally, so I'll have to put it somewhere for you. But I'll give you the video.
The link. Yes, we will be great. Thank you very much.
Thanks, everybody.
Thank you. And have a good day, good evening. Bye-bye.
Bye-bye.
Thank you. Bye-bye.